So I'm going to talk about biases in stereoscopically viewed ground terrain. And there is going to be some 3D slides in here, so make sure you have your polarized glasses just within arm's reach. Okay, so as I'm sure many of you are aware, during locomotion, you require adjusting your approach relying on an array of perceptual and motor information. Specifically, stereo provides significant advantages given its sensitivity to small changes in depth and curvature. There are many studies that show that stereo play a significant role. Oh, sorry, this is so close.
That's wrong.
I'll lean down a little bit.
No, we won't see you.
No? Okay, and yeah, so stereo plays a significant role in discriminating complex ground features. So we previously did a study that assessed the role of stereo in a very specific low hover safe landing scenario. So we had observers judge whether a terrain feature that I've shown there in the bottom right was a mound or a dip. And we had this surprising result where about 65% of observers reported seeing convex mounds, even when stereo indicated a concave dip. And in this study, we did show that stereo was critical for actually doing this type of discrimination, so it was surprising that a terrain with this shading cue could override stereo for the majority of observers. So there is a body of literature that shows there is a general preference for convexity, so why exactly do we find this surprising? So first of all, the shading cue is actually ambiguous. So it doesn't actually give you any information regarding the direction of the terrain feature. So this is an example of our high shading condition. So one of these is a mound, one of these is a dip. You're welcome to take your guess. And we specifically avoided the influence of lighting direction by randomly positioning the light source to the left or right of this feature. So we showed that binocular information like the texture and shading can actually support accurate judgments. And this one's a mound, and the right one is right one is a mound, left one is a dip. Stereo, on the other hand, can support accurate depth sign information. So observers had no problem when the shading cue was less apparent. So they performed quite well under this low shading condition. So it's not due to their inability to discriminate depth from binocular disparity. Okay, so this is when you're going to need your 3D glasses. So don't worry if you put them on, this should appear flat. So this is an example of a monocular condition, so you can see there's not much definition and you can make your guess over whether you think this is a mound or a dip. However, when we add the stereo information, you should see the mound kind of recede out from the display and you probably see a lot of depth. One fun thing you can do is close one eye so you can see how the monocular information looks and how the stereo information looks. And I think that's really apparent in this example that should recede into the screen. So at least for me, when I look at it monocularly, I'm convincing myself it's a mound, but as soon as you add the stereo information, I really see it again as what it is a dip. Okay, so given the unexpected nature of this phenomena, it was important to determine whether this bias was generalizable to other viewing environments. So our first objective was to replicate this study in a new environment and display system. So this was to rule out the possibility this bias was maybe the result of a specific viewing environment, parameters, or participant pool. Our second objective was to recruit observers that were susceptible to this bias so we can further investigate the phenomenon in subsequent studies. So here's some example of our terrain features. So I have the low shading across the top row, high shading along the bottom row, and this is a range of feature heights. So it goes from 0.5 meters up to 1.5 meters. The one thing I want you to notice is that as the feature height increases, so does the intensity of that shading. So the task was to discriminate whether this terrain feature was a mound or a dip, and we conducted this study and the subsequent studies using a MetaQuest 2 head-mounted display. So we fit psychometric functions to each observer's data. So this is an example using real data. So what I'm showing here is mound on the y-axis and the feature height in meters on the x-axis, where positive values are mounds and negative features are dips. So this is the data that we expected. So this observer is correctly identifying mounds at the high end and dips at the low end. But we had some observers that looked like this, where this observer is responding mound about 25% of the time, even though at the low end stereo is indicating a 1.5 meter deep dip. We also had some observers that were so extreme, they estimate a mound almost 100% of the time at the extreme ends of the scale. So you end up with these little V-like functions. So to measure the strength of these biases, we use the lower asymptotes of these functions. So what I'm showing you here is the pooled data. So this is the same as the previous slide where I have mount on the y-axis and the feature height on the x-axis. Along the top row is the high shading, and the bottom is that low shading condition. So we used a criterion that I'm showing with that horizontal dashed line that divided observers into 3 groups. So we established this criterion based on our previous data, but basically if observers responded mound more than 15% of the time when it was a dip, they were considered to have some level of bias. So for these observers that were no CB or no convexity bias, this is as you would expect, the bottom of those functions are below our criterion. We had some observers that had a strong bias where their tails are above our criterion. So you can see there at the low end, they're estimating mound about 35% of the time when it was a dip. And then we have our observers that were so extreme, you actually didn't get a psychometric fit. And I think at the low end here, they're estimating mound about 70% of the time, even though it is actually a dip. Importantly, what this data shows is that the lighting direction, so I'm showing the light coming from the left in the gray and the right in the red, it shows that it did not actually inform the direction of the feature or the magnitude of the bias. Okay, here's another slide. You'll need your 3D glasses. We also measured the observer's stereoacuity. So we had this high-resolution random dot stereo test that I'm showing here. So the task was actually to judge whether the top half or the bottom half of the dots appeared in front. I believe this one, the bottom is in front. Okay, good. It's hard when I can't see what the 3D looks like. So basically what we did is use this to measure their stereoacuities. So what I'm showing here is stereoacuity on the y-axis in arc seconds and our 3 observer groups along the x-axis. That horizontal dashed line is just the average stereoacuity, which is about 22 arc seconds for the study. What you'll notice is that the extreme group had significantly higher stereoacuities than the individuals that did not show a bias. So these extreme individuals had the highest stereoacuity thresholds and the strongest bias. So the magnitude of the bias does appear to be due, at least in part, to their ability to detect binocular disparities. Okay. So in this first experiment, we did successfully replicate our previous results to show that about half of these observers show this bias. So this phenomenon is quite robust despite the use of 2 different display systems across this and our previous study. So our next step was saying, okay, so why is this phenomenon actually occurring? So previously it happened most frequently with this high shading condition. So one possibility was that the disparity information wasn't visible. So you can think in this region with this dark shading, it's reducing the visibility of that texture information. And if you're reducing the visibility of the texture, you might also be degrading the stereo information as well. So the objective for our next study was to determine if this unreliable stereoscopic cues in this darkened region was actually responsible for this bias. To evaluate this possibility, we designed a terrain feature that removed half the cues by eliminating half the surface. So the idea is if this phenomenon had nothing to do with shading, this half surface should elicit a similar effect. Okay, so this resulted in 4 different conditions. So we have low shading on the left, and high shading on the right, and the light or dark half refers to which half of the surface was rendered, so either the half with the light shading or the half with the dark shading. So as a result, we get this terrain that has half the disparity, shading, and texture information as the first experiment. So we have 2 predictions. If the dark region is degrading stereo, we would predict the strongest bias in this high shading dark half condition. This is because half the surface information is absent, and the half that is present is reducing the visibility of that texture. Secondly, if we're only seeing this bias because we can't use the disparity information, if we take it away, we should also see some level of this bias. So we'd also predict some bias for the light half conditions as well, but not as strong of a bias as the dark half conditions. So what I'm showing here is the results of this first study. So I have bias on the y-axis, and again, remember that's the lower asymptote of those functions, and the 4 terrain conditions on the x-axis. So we evaluated 10 observers that previously showed either a strong or an extreme bias in the first experiment. When we got this data, we were surprised because performance was actually much better. So you'll see here that unlike experiment 1, most observers are below our criterion. So it means that observers that previously showed some level of bias don't do so for these half surfaces. To confirm this, we compared the results to the first experiment. So we have the full terrains from experiment 1 versus the half terrains here. And you can see clearly there is a large reduction in the level of bias for both the low and high shading conditions. So dividing the terrain feature along the midline eliminated this bias for most observers. Okay, so instead of enhancing the bias, observers got much better. So completely removing half of the binocular and monocular information had some unintended consequences. So for instance, eliminating half the binocular disparity information likely also made the matching ambiguity along that midline much better. And further, removing half the shading cue also likely made it even more ambiguous. If anyone's interested in discussing this further, I'm happy to do so after the talk. However, what's important here is that we showed that changing the surface configuration in this way can disrupt the bias. But these particular results did not answer our objective. So, in order to do so, we need to remove half of the binocular disparity information while maintaining the monocular information across the entire surface. And we did so by exploiting a common phenomenon known as a binocular half occlusion. So a binocular half occlusion is when you have a surface in one eye that's going to partially obscure your view of a stimulus. So for example, I have a top-down view of our terrain configuration. You can see it sticking out from the wall here. And I've added this surface to the scene that has the same color as the background. So what happens is the left eye can see around this surface. It has no problem seeing the entire terrain feature. But for the right eye, the surface is partially obstructing its view, so it can only see half of the surface. So what you end up getting is the left half of the surface is viewed binocularly, because it became viewed by both the left and the right eye, but the right half of the surface is only viewed by one eye, so it's monocularly. So this viewing geometry eliminates the binocular disparities in one half, while leaving the pictorial cues roughly unaffected. This is the last time you'll need 3D glasses. So this is an example of what that condition looks like. So you'll have that one surface blocking your view of one half. And surprisingly, so there is technically rivalry between the right half of this image, between the grass texture and the gray, but in these types of half occlusion scenarios, they are surprisingly stable. So if you have the viewing geometry that matches a natural scenario, they actually are surprisingly stable. Okay. So lastly, we once again have 4 terrain configurations, but here, light and dark refers to which half of the surface is rendered binocularly. So for example, for the dark condition, it is the half with the dark shading that's rendered binocularly, while the half with the light shading is rendered monocularly, which is why I have it slightly grayed out. So we have the same predictions as I did for experiment 2. So if the dark region is degrading stereo, we predict the strongest bias in the high shading dark condition. This is because the binocular information that's present is being partially obscured by that dark shading, and the other half of the surface just has monocular information. Similarly, we would expect some level of bias for those light conditions, but not nearly as much as the dark conditions. Okay, so once again, I'm showing the bias against our 4 different terrain conditions. The one thing you'll notice is that there's no difference between the light and the dark conditions. So regardless of whether that dark region is rendered monocularly or binocularly, it had no impact on the magnitude of this bias. So for our first prediction, we predicted a larger bias for the dark condition compared to the light, but as you can see, it doesn't seem to be the case. For our second prediction, we expected there be some bias in the light conditions, and you can see there's a couple of observers that do show a bit of a bias, but for the majority of observers, they showed no bias in the light condition. However, I do want to point out, while it does look like there could be an enhancement in the high shading condition, there is quite a lot of variability in these results, so there's no actual statistical difference between the high shading and the low shading condition. In fact, there was no difference between any of these 4 terrain configurations. So, given this bias was similar in all these conditions, it suggests that the combination of the intense stereoscopic shading and the monocular half surface actually didn't make the bias any stronger. So, was this bias caused by a lack of reliable stereoscopic information? No. So experiment 2 showed that when you cut these surfaces in half, there is reliable disparity information that can be used in both the light and the dark half of these surfaces. And experiment 3 showed that if you do have that shading across the whole surface, it doesn't actually matter whether that dark region is rendered binocularly or monocularly. So these findings suggest the reliability of stereoscopic cues in that dark, heavily shaded region is not actually responsible for this bias. So in conclusion, we did replicate this phenomenon, so we did successfully show that half of these observers demonstrated some level of this bias. Interestingly, we did show the strength of the bias may be related to stereoacuity. So importantly in this study, all observers were stereonormal, so their range was within the typical range of stereoacuities, but observers with higher stereoacuities did tend to show a stronger bias. So binocular disparity processing may play a role in the susceptibility to this bias. And of course, I showed that this bias was not actually due to the availabilities of binocular disparities. So, given these biases were quite dramatic, they may potentially be present in real-life terrain judgments, especially in impoverished environments. So, for example, in a natural scenario when you do have strong ambiguous shading, so something like sunrise or dusk, or you can think of an example where scenarios cues to ground terrain are obstructed, so you can think like mist or fog or maybe a heavy snowstorm, you could get similar shape reversals. Thank you.